Good evening, everyone. Um, Welcome to the webinar. Um, we will start after 3 minutes. Just we are waiting for a few more attendees to join, and we will start in about 3 minutes. Yeah, yeah. So, good evening, everyone. Thank you all for joining. Let me share my screen. I think you can all see my screen now. Now, let me just minimize this. All right, so this webinar is going to be a crash course for Millturn application. We will be looking at how we start from the 2D drawing, we create a 3D model, and we then create CAM part, a whole new CAM project. We define the operation, we add MCOs, we then define the channel synchronization, simulate the toolpath, and then we generate the NC code. This is what we are going to do this webinar. So this is the process flow, and this is how we are going to continue. Now, I have created a simple 2D drawing, and as you can see here, we have different operations. Like for turning, we have to do facing, turning, OD, grooving, threading, and there are a lot of milling applications. So first, we will try to create 3D model from the 2D drawing. I have created a simple DWG extension file. So with our with our SolidCAM, we have our integrated SolidWorks where we can import 2D drawings like .dwg and .txf file as sketch for our 3D model. So I'm going to do that. So click on File, Open, and we'll just go to the location where I have saved the .dwg file. Now, when I open a .dwg file, it will uh, show a window, an import window, where it will ask for the method to open this file. Here we will be looking at import to a new part as a 2D sketch. Here, since I'm going to use this sketch for my 3D, I don't want this as a reference. So I will just uncheck that and we'll click on next. Here, I just want this view, and the remaining views I'm going to eliminate. You can also import the dimension by clicking on this, but I'm just clicking on uncheck. We click on next, and here we have the option to remove the entities. We can just create a window and then say remove entities. Again, create a window and say remove entities. Now that I have the view that I want, I'll just say finish and I'll click on yes. So now I have this 2D drawing as sketch in SolidWorks. Now all we have to do is trim this lines, because I just want to get the cross section of my turning part, not the whole part. So I'll just delete all these, and few more things to note. When you are importing a .dwg extension file, uh, your scale or the dimension will not be as per this model. It will be scaled 4 times or 3 times as per the sheet properties. So now let's check the dimension here. We go to the smart dimension. So here you can see the dimension is now 450. In order to scale back to this dimension, we will use the scale entities option here. So we will just select the whole thing and then click on scale entities. Here I'm going to say scale about, and I'm just going to click on this point. Now I have set this to 0.4. The reason being is since my dimension should be 180 and the dimension I have right now is 450, I just divided it and then I got the scale dimension. So I have given it 0.4. So it has shrinked to my sketch to the 0.4 mm. Now we will go back. Here we will do one more thing. First, we will fix this whole sketch. The reason being is since I don't have any dimension here, it is not constrained. So if I fix this sketch, now if I move, it won't move easily, or it won't move at all. So now I will set this point to the origin. Okay, to do that, we will use the move entities option. So which entities to move, I will just select the whole sketch, and I'll set the start point as from this point to this origin, right? So now I have my sketch. I just have to create this as my construction line, or you can just close this. Now we will click on the features and we'll use the revolved option to revolve this sketch. Now that I have all the basic dimension or the revolved part, I will still need to add 3 more features, 3 more milling features in fact, and then we will continue to the CAM. So for this, let's take this feature. So 17 at a degree of 40, and the width is 46. So let's go to the front plane and add the sketch. Right. Then I'll just add a center line here. And we give a dimension of 46 as per the drawing and a 17 mm width for the pocket, and the degree is at 40. I'll just extrude cut this whole feature, and the condition that I'm going to give is through all both directions. I think I have missed. No, it's correct. Now that we have done this, we will add 2 holes here. So as per this drawing, so this 2 holes is 20 mm apart, 9 mm from this side, and the hole diameter is 6. So let's add that. I'm going to use hole wizard. So for this, I'll just create a sketch on this plane, add a center line, and from this edge, it's 9 mm. I will just create a center line and then create 2 points which are 20 mm apart. Then we'll give a symmetric relation, and that's it. Now we go for the hole wizard. To define the 6 mm hole, we will just select the hole type as simple hole and the size as 6 mm diameter. Blind, I'm keeping it as it is 10 mm. The position that I'm going to give is this 3D sketch and click on OK. I'll hide the sketch now. Now we will go back to the second milling feature, that is this one, which is at an angle. Or yeah, we'll just do this. So I'll just rotate this. Okay. So now this is at an angle of 70 degree, and the distance is 77. There is also a degree here, 15, and 13 mm distance apart. So let's create this. This will be in the top plane, and I'll just create a center line again. Give a distance of 77 and a degree of 70. Then I think we need to give this distance, okay, 13 mm. So let's just create like this. This will be perpendicular to this one, and the dimension will be 13 mm, and this was 15 degree. And this depth is 5 mm. And this is 4 mm. Right, so now it is fully constrained. I just need to revolve this feature. So let's give a relation parallel, right? And then we go to the feature revolve cut. Yes. And I'm going to give this as my revolution axis. Fine. And again, hole wizard, I think there is a hole here, and this is of 6 mm. Again, I'll be giving a depth of 10 mm. So we go to 3D position, sketch, again like this, click on OK. Now there is last one milling feature remaining, or a pocket remaining, that is this one. I will rotate it back to normal. Yeah, this one. So here we have two radius arc, and which is at 12 mm radius, 45 degrees, and the center of the arc is 8 mm from the center point. So let's click on this face, and we'll select this and this as my 45 degree. Now I will also add another center line, a midpoint line in fact, with the construction geometry, and I'm going to give a relation perpendicular to this. This is because I can give a mirror property. So for this, now we will select the center point arc and give this from start point, and this is the end point. Give the radius, that's 12 mm, and from this point to this point, it's 8. Now we will just mirror this about this center line, and that's pretty much it. We'll just cut this. At this depth is, I think, 5 mm. Yeah, this depth is 5 mm, and I will say flip side to cut. Let's click on OK. Here there is a radius of 12, so I'll just add this fillet, and this is 12 mm. Give this edge and this edge. All right, so I think we are done with the 3D model. Now we'll create a CAM project. So let me open this presentation. Now, before we create a CAM project, I would like to discuss some this machine that we are going to use for this project. This machine is having a dual spindle, and it's having two turrets. The upper turret is having a swiveling head, which is B-axis, and at the bottom we have a turret. So for this example, I'm going to say this will be our turret A, and this will be our turret B. And on the left hand side we have a main spindle, and on the right hand side we have a back spindle, or we can call it sub spindle. Now the upper turret has 4 axes. It can move in X. As you can see, this is our Z axis and this is our X. It can move in X, it can move in Z, and also it can go front and back in Y. This turret also can move in B axis, while the lower turret, it only has 2 axes. It has X and Z. It doesn't have Y. And this spindle has C axis, and the back spindle has W, that is, it goes towards this main spindle and away from the main spindle, and this also has a C-axis. So all in all, it has 9 axes. So we and the reason why it is called dual channel, because there will be 2 channels to execute this program, and that's why I've taken this example for this project. Now, Millturn machines, there are variety of different types. Like, it can have just the upper turret, just the main spindle. It can also have just dual spindles like main spindle and back spindle and the upper turret. The lower one can be a steady rest. All this kind of configuration SolidCAM supports. For now, we will be looking at this project or with this machine. So let's just uh, create a new CAM project. So we go to SolidCAM, new, milling. Just a minute, I will just save this part. File, save. I'm going to save this. Now we go to SolidCAM, new, and not milling, we have to do Millturn. So we will go for Millturn. And here we will be moving to the next step, that is defining the CAM part definition. So defining the CAM part definition, these are all the regular routine process which we do in the milling application, where we just select the machine, coordinate system, stock, and the target. The only difference for the Millturn is that you have to define the machine setup. This is very important for Millturn application. And here we have to define the fixture for main spindle in the main spindle section. You can define the jaws, or if you have any 3D model as fixture, we can do that. We can also define the fixture for sub spindle here in the back spindle. And there are even subsections in the main spindle, that is main spindle post 1, and there is subsection for back spindle, that is back spindle post 1. Here in the subsections, we define the part holdout from the spindle. So these two options are very important for Millturn, because if you don't define this correctly, your part transfer or your setup will not work properly. So we will look at this. First, we will define the machine. Okay, so just a minute, I will just check if I have set the correct location. Yeah, all right. So SolidCAM, Millturn, click on OK. And here I'll be defining the machine. That is, in this example, I'm going to take a Okuma Multus U3000 machine, and the coordinate system that I'm going to set here is for the main spindle. Okay, so when you define the coordinate system for the main spindle, SolidCAM will take the second spindle's coordinate system automatically. So we will see this. So we go to the coordinate system, and we will say place coordinate system origin to, and say center of revolution face. We will just select the face, and I have decided to do this area first in the main spindle, and the remaining area, that is the backside portion, we will be doing it in the sub spindle. So just a minute. Yeah, I'll just click on OK. And you can see it has created 2 coordinate system. One is Mach1 position 1, which will be for the main spindle, and the second, it has created Mach2 position 1. So let me go to the coordinate system again. So this is done automatically by the software. Now we click on OK and we define the stock. As you can see, there are 3 green ticks already, just because I have set in my settings page where it defines stock and target automatically. So I'll go to the stock section and define the material here. The Z minus material, it has taken 10. For this, I'm going to keep 5 mm extra material, and I'll click on OK. That's it. And the target, it's already defined. Whatever body is available in this CAD area, it will take that model as your finished part. So I'll click on OK. Now we go to the important section, that is defining the machine setup. So here we go to the setup here, and we will define the fixture for main spindle and back spindle first, and then we will define the subsections. So for the main spindle, we'll click on here and say new, and here we can define the job parameters. So I will be keeping this as 60 mm job width, jaw height as 60, step width 20, and step height also 20. And then here for the back spindle, again I will say new, and I'll define this as 60 and 20 mm. Same jaw parameters for main spindle and back spindle. Now in the subsection here for the back spindle, since we know that the coordinate system for the back spindle is Mach2 position 1, we click on this and we set this to Mach2 position 1, and then we come to the next important process where we define the part holdout from the spindle. So we go to the main spindle post 1 here, and we click on the machine preview, and here in the machine preview we get to see how much part we need to hold out from the jaw face. Okay, so this distance is actually the distance between the coordinate system. If you are defining the back spindle position 1, the distance will be from the coordinate system to the jaw face. So here first we will define the main spindle's holdout. And here we just have to click on this box, and you can just scroll down and see the part moving outside. So for this example, I'm going to keep 125 mm outside this face. Okay, so from this coordinate system to this jaw face, the distance is 125 mm. The same option, the same process, we do it for the back spindle position 1. We click on the back spindle position 1, and here we again click on this box and scroll down. So 65 mm, I'll keep it outside from this face. I'll click on OK here, and we are through with this CAM part definition. The next process is we define the operations. So now to define the operation, we'll start with the main spindle here, and we will start with facing, and then we will do OD turning. So we click on face, and we click on new geometry here. And for facing, as you can see, when you define the stock and target, SolidCAM defines this envelope. Now this envelope is useful for defining the geometry for our operation. So when I click on new geometry, and if I select the wireframe, I can just select this this edge for my facing, and you should check if the direction is from top to bottom. Since facing, we do it from top to bottom. Direction is important, and we go to the modify geometry. Here we give extension. So just a minute. Okay, so here we give the extension. I have extended automatically from start to stock till the end of the stock. Then we go to the tool page, and I'll select. Here we will define the holder, and I'm going to define the holder which is downloaded, and I will import that download holder onto this project. So to do that, first we will just open that part which I have downloaded. Let's open that. I think it is the webinar. So here I have this holder here, and I'll just expand this assembly view, and we will just hide this insert because we are just going to import the 3D holder. So now for this, for importing this holder, we have to first define the holder mounting position, and we have to define the insert mounting position. Okay, so holder mounting position is the position where your holder is mounted on the spindle, and the insert mounting position is the position from your holder mounting point. Okay, so it would be here. So first, let me define the holder mounting position. So we go to the assembly, and we click on reference geometry and click on coordinate system. I have an origin here, here which is already set in the 3D model. I'll just have to click on this origin and click on OK. Now so this will be our holder mounting position. Now to define the insert mounting position, we have to create a point. So the need of creating a point is just to know the distance from the holder mounting point. So we'll just click on the top plane, create a sketch, and I'll just click on this point or create a point, and then we will just measure this value. Okay, so we go to the evaluate, click on measure, and we'll just select the coordinate system and the sketch. So the distance is around 105.6 mm. Now we will just note this value, that is 105.6. Now we'll just say save as, and I will save this as STL. Okay. Before saving this as STL or clicking on save, we should ensure that in the options page, it is set to do not translate STL output to positive space. Okay, and we will say the output coordinate system as the coordinate system 1, which we have created. We'll click on OK, and we'll save this. Okay, and then we will import that holder in our project. So let's click on this. Now for this example, I'm going to create facing with a CNMG tool. So we'll click on the profile insert, and here I'll give a name CNMG 120408. When you just type the name and the specification, all the areas here gets filled automatically. And here we will define, or we will add the holder. So I'll just say add holder, and we will go to the holder and to the topology page, and we will import this STL file. Now we go to this. When we click on this, this folder is actually set in the setting. So you have to ensure that whatever STL holder that you had defined, you have to copy this and paste it to that location. So we will copy paste to this location here. Okay, so this will be our holder, and I'll click on open here. Now we go to the tool picture, and you can see the holder is visible, but the insert is not visible. The reason being is we have to define the insert mounting position. This we define it in the joint section of the holder, and in the Z we say minus 105.6. When you click here, you can see the insert is added onto the holder. We'll click on OK, and I want the tool to be in 45 degrees, so minus 45 degrees, to machine this with turret A, or the swiveling head. We click on the technology page, and here I can give the depth of cut. So I'm keeping it 1 mm, and I'm going to finish it with the same tool, and I'll just save and calculate. Okay, just calculate again. Okay, so we can just see the solid verify, or we can go with the host CAD. So this is how it is going to do. This is a roughing pass, and then this is the finishing pass. We are going to use the same tool for the turning as well. So again, we go to the SolidCAM turning tab, and we click on turning, and we go to the new geometry. So we select the first edge and the last edge. So this will be my first edge. We'll change the direction, and this will be my last edge. Use modify geometry to extend this chain to the start of the stock, and also I'll give some extension here, a 3 mm extension at the end. I'll be using the same tool. So we click on tool number 1, and I'll give a minus 45 degree. Now here we will not do the finishing. The finishing we'll be doing it in the later stage. So I'm going to keep the strategy to the non-descending motion. The reason being is, if I keep it descending motion, it will go inside the groove. I don't want that to happen, so I'll keep non-descending move and say save and calculate. Okay, so now we will create another operation, which will be the pocketing operation. So for the milling operation, let's see, I'll create for this angular pocket. Okay, so this also I'll be doing with the turret A. So notice that when you are adding an operation with the turret A, your sub machine is automatically selected by SolidCAM. So you can see that these two operations are done using turret A on the main spindle. Okay, so this is very easier for us to understand which operation is doing it with which sub machine. Okay, so we go to the 2.5D, that is for milling operation, and we'll select a pocketing strategy. So we click on pocket, and click on new geometry. Before defining a new geometry, we should ensure that when you're defining a pocket strategy, your Z should be perpendicular to that face. So we'll have to define a new coordinate system. We'll add, and I'll set the place coordinate system origin to coordinate system #1 and select this face. Okay, right, and then we'll define the geometry. For the geometry, I'll be defining or I'll be creating a sketch. So click on this face and we'll define this circle. So my pocket will be within this pocket circle. So I'll just define this sketch as my geometry. Now we go to the tool, select, and in this operation, I'm going to use an end mill. So just double click on end mill, and you can see that the end mill is added on to the magazine. So this section is of turret A, and the bottom section is of turret B. So whenever you're going to add an operation to the turret A, just click on the tool near the turret A, and your tool will be added in the turret A section. Okay. So now the diameter, I'm going to take a 13 mm, not so standard, but still the pocket distance is 13. So I'm just going to finish it with the same diameter. I'll click on OK. Before that, let me add the holder. So right click and say add adapter and holder. Here, I'll just select ER32. We can click on the picture window and you can see the tool image with the holder. Then we click on the levels. The upper level, I'm going to give it this distance, and the pocket depth, I'm going to give the bottom one. So just a minute, let me check. Okay. The depth of cut, I'm going to give it 0.5, and I'll just save and calculate. Now the remaining area, the remaining section, I'm going to do it with the profile strategy. So we'll click on profile, and we'll define this chain. And we'll click on this tool, since I'm going to use the same tool for machining this profile. The upper level will be this one, and the bottom level will be this area. In the technology page, we will just check the geometry. This looks good. I'm going to use the helical pass, and the depth of cut per pass will be 1 mm, and I'm going to give a 1.5 mm so that it will go in 1.5 mm delta from this level. Okay. Lead in, lead out, I'm going to set to none, and I'll just save and calculate. Right. So we have a very good feature in SolidCAM, which is updated stock, where you can click on the updated stock and you can just drag this box. So when you click on this box, you can see after this operation how much is the material remaining. So you can just drag this box to the end, and you can see this is how the machining is done. We will then define this area. So here I'm going to use a profile strategy again, and this time I'm going to use this geometry, and tool, I'll be defining a new tool which is an end mill of dia 8. Okay, so and I'll add an adapter and holder, and the holder I'm going to keep it ER16. Okay, so we'll just check the picture. This looks good. I'll click on OK. I think the holder is not added yet. Just and then we can just check the machine preview. Okay, the tool image. Click on OK, and we will define the levels here. So the level will be from the top. I think I defined the wrong geometry. The geometry should be from the smaller one. I'll be defining the smaller one here. Okay. Fine. So the levels, this will be my upper level, and this will be my bottom level. Now here, I'll be using another feature in 2.5D, which is giving a draft angle with the profile. So we can just select advanced and just give the draft angle to 15 degrees. Okay. And we can just give the depth of cut of 0.5, or let's give it 1 mm. Since I'm going to give just the roughing pass, this is not the finishing pass. I'll set this to none, and I'll just save and calculate. Now in 2.5D, as you can see, there is a lot of lifts. If you don't want these lifts, you can do this in HSS as well. So I will delete this and create this in HSS. I'll just go to SolidCAM 3D, click on HSS, and use constant Z. Here, I'll be just defining this surface, and we'll define the tool. Eight mm, and the step over, I'm keeping it 1 mm, and the sorting, I will be keeping it spiral. And in the links, I will just say use lead in, use lead out, and the automatic arc, I'm keeping it 1 and 0.5 mm for the radius and arc. Okay, so this looks much better. So this is the roughing. So this is how my machine stock will look like after this. And the remaining, this finishing, we will be doing it with the multi-axis operation. So we will click on multi-axis. We'll use simultaneous 5-axis since we have a swiveling head. So we will use a simultaneous 5-axis, and we go to the projection strategy, and we'll click user defined. We define the corner system to Mach 1 position 1. The drive surface will be this one, and the projection curve will be this one. For the tool, I'm going to select the same 8 mm end mill, and I will keep the tilt angle to 90 degrees. So I'll just save and calculate. I think it looks good, except I need to give the lead in and lead out. I'll just give use lead in, use lead out, and the automatic arc, I'm keeping it 1 and 0.5. Okay, so this is how it will look like on machine. So when I click on the machine simulation. As we have seen, we have the upper turret, the lower turret, the main spindle, and the sub spindle. Now we will just reduce the simulation speed and we can see how it's finished. Okay, so this is the benefit of having a head. If you have a 5-axis part, it can be done using SolidCAM multi-axis. Now we will define another operation. This will be for again another milling operation for this pocket. So we'll use 2.5D here, and we will be using profile, and we'll click on we will define this chain as our geometry. Okay, and we'll select the tool. I think we have to define the coordinate system. So we'll just go to the coordinate system page, add, and select this page or this face. Click on OK. We'll define the geometry. Click on this one. And we'll define the tool. Going to use the 13 mm end mill here. Okay. And the levels, it has been already set. I'll just make sure by selecting this face. In the technology section, I'll just check the geometry. It's left. I'll just reverse this chain, and I will do a roughing. Keep it 0. The depth of cut will be 1 mm, and the clear offset I'm going to give a 6 mm so that it will add another pass on the outside. Click on none, and then I'll give some extension at the start and end here in the geometry section. So I'll give 7 mm at the start, 7 mm at the end, and I'll just say save and calculate. Here I'll keep it zigzag, and so you can see and in the link, since it is lifting at after every pass, you can go to the link between passes and set the level of current path. Since it's outside, there is no problem if it goes in rapid. So we will just check. Yeah, this looks good. Then we click on another operation or we will add another operation here on this face, that is this taper face. So we'll click on profile. Again, we will add another coordinate system here. We'll just say add. We will select on this face so that my Z is perpendicular to that face. And we'll add another geometry. So this will be my geometry. We go to the tool, select, and we'll be adding the same tool, that is 13 mm and mill, and we'll define this as our depth. Okay, so I'm just keep this will be our depth, and the technology, I'll just check the geometry and give some extension of 7 mm at the start and at the end, and I'll give a step down of 1 mm and this will be directly finishing here. I'll just keep the lead in and lead out as none, and we yeah, and this is how the simulation looks like. All right. Now we will add the remaining turning operations here, that is for grooving and also finish turning and then threading. So for this, I'll be using the second turret, that is turret B. For that, we go to the turning section here, SolidCAM turning, and we'll select grooving operation. In the grooving operation, we'll define the geometry for grooving. This is start, and this will be our end edge. So when I select the first edge and the last edge, all the edges in the between is selected automatically. I will extend the stock. Just using auto extend start and auto extend end, but I'll be extending it along X, so I have to click on this option X plus. Now we go to the tool and we select grooving tool here. So for grooving tool, since I'm going to add this in the turret B, I'll just click on turret B and I'll click on external grooving. The insert width will be 4 mm and this width will be 3.5. We click on the machine preview to check how this tool is set on the machine. So you can see here, and if you focus the tool, by clicking on the first icon, you can see that the direction is not correct. It should be along X. To do that, we go to the shank, that is external grooving shank, and in the joint section, we define RY value to 0. So by doing that, your tool will be aligned to your X-axis. And here we will be defining also how your tool is being positioned. So in this example, I'm going to keep the tool to 25 mm plus, just because I have a shank of 25 mm, and yeah, so instead I'll just give the direction. I have to set the direction, sorry. I'll keep this to left, and in the joint section, I'll keep this to -25. This is how I want, because your shank should be behind your origin. Okay, so this you should take care. Now we will click on OK, and we will go to the technology page and define the grooving parameters. I'm keeping as it is, but in semi-finish, I'm going to use a turn groove method for grooving, and we'll just save and calculate. So this is how turning will be done. I'll be doing the turning simulation. The roughing part, and then the finishing with the turn groove method. Now we will add the next operation, that is the finishing operation, the finish OD turning operation. We already have the operation, the roughing operation done with turret A. I'm going to finish this with turret B. So we'll just copy this operation and we will paste this after grooving. All I have to do is change the tool so that my submachine changes from turret A to turret B. So we click on tool, we'll select, and as I mentioned, to add a tool in turret B, you should select a tool in the turret B, and then we click on external turning. So here we will say CNMG, again the same 120404, and in the joint section, make sure your RY is 0, and just click on the machine preview to check the tool placement. It looks good. Here I'll ensure again if the direction is correct. So here the shank that I had defined is right. I'm changing it to left, and in this page I will set the distance to -25. Again, the same process, your shank or your insert should be behind your Y. Okay, so I'll just click on OK, and we will define the turning operation. We'll set this to finish only and finish on the entire geometry. So I'll just save and calculate. Right, so now comes to the next operation, that is threading. So for threading, we again go to the SolidCAM turning page. We define threading operation and we click on new geometry. This will be my edge, and I'll click on OK. In the modify geometry, I will give an extension at the start and at the end. So here I'll give a 4 mm extension at the start and 4 mm extension at the end, and I'll click on OK. The tool that I'm going to use is a threading tool, which is for creating a thread of 45 by 1.5 mm pitch. So we click on the turret B tool, and then we will add an external threading tool. Here we will define the external shank will be on the left hand direction, and in the thread type we will select isometric, and since the thread that I have is M45 by 1.5, I'm going to select the same. Okay, no reason, you can just the reason why is when you select that, you will get the insert according to this metric standard. So you get the pitch here. You can just change the value of H here to 20 and just click on the machine preview to see how your tool is placed. Again, we will have to change the direction. We go to the access page and we click on RY and set to 0. This looks good. Again, I'll have to give a -25 mm. The 25 mm is my shank width, and this looks good. I'll click on OK. We go to the technology, and here again I will define the metric standard in the technology page. I'll set this to M45 by 1.5 and I'll click on OK. The reason being is it automatically sets my minor diameter, and also the pitch is read by the standard that I've selected. Okay, so I'll just save and calculate, and you can see the threading operation being performed. 4 mm, I have just given an extension. You can just reduce that extension. We can just check how the turning or the threading operation is done using solid verify. So I'll go to simulate. I'll click on solid verify and just play this. Okay, so this looks good. We go back to the remaining operations. Let's add the remaining operations. I think milling operation is still remaining. Okay, so we will be creating operation on this page or on this phase. For that, we will be defining pocket or pocketing operation on turret B. Now, as I mentioned before, the turret B has only X and Z axis. Now, to mill this pocket, you should have X, Y, and Z, but we have an option where we can define the output in polar or Cartesian mode. So in the 2.5D section, we have a page which is of motion control. You can just click on the fourth axis and define the coordinate type and set your plane. The output will be in XZC or YZC depending on the plane that you choose. This option is very useful for the turrets which doesn't have y-axis, or when your turret is having some limitation with the y-axis if the limit is crossed. So you can use this option, that is fourth axis. We'll use this. We'll click on pocket in the 2.5D. Okay. And the coordinate system, I'm keeping it Mach 1 position 1. I'll select the geometry using our smart face technology, where when you have both the chains in one single face, you can just select that face and it automatically selects all the chains in that face. We'll select the tool, and the tool I'm going to select first. Click on this tool in the turret B section and then add an end mill. So I'm going to add a 12 mm end mill here. Okay, and in the machine preview, we will just check how the tool is set. We go to the access page, and here we will define a holder. So first, let's define a holder here. I'll just click on add holder, and in the turning STL holder, let's select this one. Okay, it looks good. Yeah, that's pretty much it. We'll click on OK, and then notice that the RPM is not set here. The reason being is the station that I have defined doesn't have the option of live tool. So certain in different turret, there are certain stations where live tools are not allowed. So we click on that station which has the option of live tool. So in this machine, the station 8 has the option of live tool. So we click change that to station 8, and then you can see that the RPM is being calculated. So now rest everything, I'll just set this to step down to 1 mm. Open pocket, approach from outside is set. And in the motion control page, I'm going to set fourth axis, and the coordinate type, I'm keeping it Cartesian. Okay, and I'll just save and calculate. So this is how the simulation looks like on machine when you are using the fourth axis option. So now we click on the front view and I'll zoom on, and this is how it looks like. The machining is done in X, Z, and C. All right, so I think we have done the operations on the main spindle. I think only just the holes are left, so we just add whole operation using another feature of SolidCAM, which is hole wizard process. So for that, we go to SolidCAM AFRM, and we have an option which is hole wizard process, where we just select the hole, one hole, and whatever hole is available in that uh, uh, phase, or which is being created with hole wizard, it will select automatically. And when I click on OK, it will add operations. So you can see automatically it has added operation for the hole type I have. So it has added spot drill, and it has added operation for the drilling as well. Okay, I'll hide the sketch. Okay. Again, we will define a hole operation on this angular face. We'll just click on hole wizard process, just select on that hole, and we'll click on OK. Okay, right. So it takes automatically the depth of the pocket, uh, all the operations, and also it takes the diameter of the tool automatically. Okay. Now we will now if you don't want this spot drills, you can remove this by but when you remove this, what happens is that since you have created with hole wizard, this are created in groups, so there are chances that this will also get deleted. So for that, we need to explode the group or remove the group. Just right click on these operations and go to the operation group and say explode. So now you can delete these two operations. Since I have a flat area, I don't need this spot drill, and I'm using a carbide drill. Okay, so yes, that's pretty much it for the main spindle side. Now we will be looking at the next section, that is defining the machine control operations. Now if I check the machine simulation of all these operations, we'll get to know one thing, that there are certain areas where we have to retract the turret A to the home position, and after the turret B is finished, you have to retract the turret B to the home position. So we'll just click on the front view and simulate the whole operation again. Okay. So this is the facing, turning, milling operation. Now here, when it is doing, there are chances that this can collide. So it is always the better practice to move your turret A to the safe position before your turret B operation. Okay, so to control these machine elements, we have an option called machine control operation. So machine control operation is nothing but operations to control elements like steady rest, tailstock, sub spindle, main spindle, and part catcher. So if you want to define the turret A to retract to the home position, all you have to do is just click on turret A and give the movements, and using the machine preview, you can see how the turret A moves back. Okay. In SolidCAM, we have instead of defining each step manually, like if you see here, you have to define 3 steps. First, you have to retract in XY, then we have to retract in Z, then you have to retract in B. So all this is a tedious process. So in order to optimize this process, we have created this templates where you can see turret A retract. It in turret A retract, it has all these movements available. So you just have to click turret A and just save and exit, and your machine control operation is added. It moves your turret to the safe position. So you have strategy for or the template for part transfer from main spindle to back spindle. You have the template for the steady rest, for the part catcher, and also to eject your part from the back spindle. All these templates are available in the Millturn post. So now we will go back and we will keep adding the machine control operations. So as I said, before turret B, we will add a machine control operation to move your turret A to the safe position. For that, we will click on the uh, operation at the end of turret A, and we will go to the MCO icon, and here we will click on this and say turret A retract, and we'll just save and exit. Okay, again after the end of the turret B operation, we will again add an MCO and we'll say turret B retract. Okay, and then we will add an operation that is turret A retract. After this, that is in the MCO, we will say turret A retract. Okay. Now the next process is, after all the operation in the main spindle, I want to create operation for the sub spindle. To do that, I have to transfer the part from the main spindle to sub spindle. So we go to the MCO and we go to the templates and we'll say part transfer from main spindle to back spindle. Now in this MCO, we have in the templates, we have some options. So we click on the machine preview and we'll see what those options are. So here we have to set the rapid pre-positioning. So the rapid pre-positioning is nothing but your back spindle will move in W axis in rapid to till this safe position. So when you click on this rapid pre-position, it is set by default to minus 1400. If you don't want this, you can also just click on this W axis box and you can use the scroll button in mouse, and you can just check if this is what the position you need, and then you can use the paste axis value. So when you use the paste axis value, this value is pasted on this option. Now clamp position by default will be in your setup location. So this is why the machine setup is important when you define the position for your back spindle and main spindle. So if this is not correct, your part transfer will not be correct. Okay, so this is correct. I'll just click save and exit, and then we will add operation for the sub spindle. So we will use the I think facing and turning operation. So we'll click on face, and now we will be using the Mac 2 position for my sub spindle, not the Mac 1 position. Since we are going to create operation for the sub spindle, we will be selecting Mac 2, and we will be defining a new geometry here, and this will be my new geometry and will extend the geometry from start to the end of this stock. We define the tool, and this time I'm going to face using turret B. So I'll have to define the tool first. So I'll be adding an external turning tool. Let's keep it CNMG 120404, and I'm going to use the shank direction. Just a minute. I'm going to use the shank direction to left, and we will just check the machine preview how it looks like. Okay. Again, the placement is wrong, so we go to the joint section, or sorry, the quick access, and we will set RY to 0 so that my tool is aligned to the x-axis. Now, since I'm going to machine my on the back spindle, the insert is still pointing towards the main spindle. So to change this, we will rotate this along x. So this is x. So we will rotate x along x to 180 degree. Okay. So now this looks good, but now we will have to check the positioning. So we will check the position here. Just a minute. So here we will be keeping it to 25, so that when so that this is your insert is along the center. Okay. So I'll just click on OK, and we will define the technology. I'm keeping it 1 mm stock, or sorry, depth of cut, and I'll also be defining the finish, and the approach and retract will be from right safety corner and to the right safety corner. So if you check the Z axis, your right safety corner will be on this side. Okay, so I'll just save and calculate. Okay, and we'll just check this host CAD simulation, how it looks like. Okay, still the alignment is wrong. We'll select. Again, go to the machine preview and we'll check how it is. Just looks all right. Now it's correct. All right. Now we go to the next operation, that is turning. And again, we will define the first edge and the last edge for my OD turning. Okay, so this will be the direction. I'll reverse my direction and then this one. We will modify the geometry and set the geometry auto extend start and auto extend end to stock. We'll be using the same tool, T4. Okay, again, just let me check. Okay, looks good. And we will define the strategy for turning, the parameters. So I'm keeping a depth of cut 1, and I will be doing the finishing afterwards. Okay. Strategies, I'm keeping it non-descending motion, and in the link, I'm keeping it from right to the right. Just a minute. Yeah. All right, so now we will be defining the next operation, that is the last operation, which is the grooving operation. So now here we will be using trochoidal turning, another concept of turning, which is using the concept or a similar concept, not the exact concept, but a similar concept to eye machining. So using the Mac to position 1, I will be selecting this as my chain for geometry, and then in the modify, auto extend along X, auto extend along X, and then we'll define the tool. The tool I'm going to define is on turret B. So I'll click on this tool and select external grooving. Insert shape, I'm keeping it round, and I'll be using a 6 mm round insert. Shank, I'm going to define the direction as left, and we'll just check the placement of the tool with respect to the turret. It's RY, I have to keep it 0 so that my tool is aligned to the X. Okay, this looks good. Again, I'll have to keep this -25 so that my insert is pointing along the center of the spindle. Okay, so I'll just click on OK. And then in the technology page, here we will be defining the minimum cutting angle and maximum cutting angle. So based on the values that we input here, the step down is calculated. So I'm going to keep it less. I'm going to keep it 30 to 40 degree, and then I'll give a semi-finish finish operation. Okay. Then here also in the links, make sure you have your approach and retract to right safety corner. Okay. By default, this is set to left. We have to set this to the right safety corner. Then this will be the last operation, which is the turning operation. We finish turning operation. We'll just copy this and we'll paste it at the end of after the trochoidal operation, and double click this operation, and we'll just set the technology to finish only. And here I'm going to say finish on the entire geometry. Okay. Links, I think it is, since I have copy pasted, it is my default set to right safety corner. All right, so now that we are at the end of defining operation, let's look at the next step, that is adding channel synchronization. So channel synchronization is useful when you want to simultaneously perform machining on both the spindles. Okay, so the advantage is that you don't have to keep the spindle idle, and you can also see which operation you can simultaneously perform on both sides. Okay, we also have an option that is clash view. So if you have done these two operations simultaneously, there will be a clash view, and when you click on that operation, it will show that this operation is colliding with the second channel's operation, and it is because of the C1 axis. So you get all this information in channel synchronization. Very useful for those which have machines with a dual channel system, and you can also optimize your cycle time. So we will see that here in the project. Now after this, after the end of the operation, we will add another MCO, or rather we call it machine control operation, which is to eject the part from the back spindle. Okay, so we click on MCO and we will select the back spindle, and then we will click on the clamp, and here I will set this to release stock. Okay, so that uh, on the part on the back spindle is released. Okay, now we go to the channel synchronization. For that, we right click on the setup and we click channel synchronization page. Now here we will fit this by clicking on this first icon and say actual size. Initially you will have this many operations and there are a lot of labels. We will first delete all. Okay, so we will use this option delete all, and you can see now all this operation that is on the turret A are on the left hand side and on the turret B are on the right hand side. We will use this option, that is it will synchronize all the operation as per your CAM manager. So when we click on this, you can see that uh, as per your CAM manager or your uh, definition of your CAM operations, it is shown here. Now you have to say back spindle. You have to click on this first operation of the back spindle and say right click and say add new workpiece. Okay, so when you click on that, your operation starts from the back spindle. Okay, so this is a standard routine process when you are having a channel synchronization. We delete all and we use synchronize all operation as CAM order. We click on this icon and then we right click on the first operation of the sub spindle and say add new workpiece. Okay, and here now you can see that the total machining time taken is around 36 minutes 40 seconds. Now what we can do here is you can try to remove the labels. Now these labels are nothing but the weight marks. Okay, uh, when you have these two weight marks in sync, only after these two labels are finished, the next operation is performed. Okay, so now I will just delete this label here so that all the operations on between these two labels and between these two labels on the turret B are simultaneously performed. Okay, and again, now if you see here, this is the operation clash view. It is currently grayed out. This means that there is no clash as of now. That means the turret A operations, all these operations and all the operations in the turret B, and the first 5 are running simultaneously and without any clashes. Now again, let's see, I get too greedy and I will just say I will delete this one and I will just check if this works. Now if I delete this, it will show this icon. This icon is activated, which is the clash view. When I click on that, it shows that these operations cannot be simultaneously run with these operations. Okay, so we will go back, we will delete all, again synchronize, add new workpiece at the start of the sub spindle, and then we will delete the synchronization label at the start of the turret A operation. This looks good, and now you can see that your machining time has reduced since all these operations are running simultaneously. So from 36 minutes to 25 minutes, it has reduced using channel synchronization. We'll just save and exit, and we'll check the simulation of all these operations. You'll get the idea of the use of channel synchronizations. All right, so we click on the front view and I will just drag this. Okay, Now, if I run this, you can see that at a time, the turret A is working on the main spindle and the turret B is working on the back spindle. Okay, so this is in sync automatically, and this is how you can reduce your cycle time and also optimize your process using channel synchronization. So this is the toroidal operation performed. And then the lower turret goes to the main spindle and it performs the remaining operations. And then there is this part transfer and then it's done. Okay, so this is how all the operations simulation looks like. Here, I would like to add one more thing. In the channel synchronization page, you have a section where you can see the cycle time for all the operations here. Okay, so depending on which operation it takes too much time, you can try to further optimize, or you can try to add simultaneously another operation on the other turret to optimize the cycle time. Okay, right, so we are at the end of the webinar. Thank you all for attending. If you have any doubts, you can write down or you can send a mail to my mail ID. I'll just write down my mail ID here. Okay. So this is my mail ID. So if you have any doubts, you can just write a mail to me. I'll try to answer all your questions. Thank you all for joining. Have a great day. Bye-bye.